Okay, so mountains, air going up, cooling down. Another way that we can get a lot of air moving up is if we've got two different masses of air, different temperatures, kind of like we saw ocean, we can have different water masses, and these come together, say one's cool, denser air, one's more lighter air. When they run into each other, warm, less dense air, that's going to move up. As it moves up, it's going to cool, and we're likely to see clouds. What types of clouds? Well, the convection pattern tends to make cumulus clouds. We see this quite a lot. As the weather gets warmer, on a warm summer afternoon around here, you very commonly see a buildup of cumulus clouds, maybe even build to the point of making a thunderstorm. Again, that's just because Earth's surface is not all the same. We've got some places with a bit lower albedo, they warm up more, or perhaps the sunlight's coming more directly due to the slope of a hill, things like that. And so we've got this warm spot, ground warms, air above it warms more, that warmer air rises up as a thermal. And eventually gets high enough that rising air cools down and reaches the dew point, and we make this cumulus cloud. Air is rising, so it tends to puff up that cloud, give that standard lumpy pile of mashed potatoes look to a cumulus cloud. Of course, other air is sinking. The gaps between the cloud are where we have cooler sinking air. As we noted before, this happens where we've got a large body of water next to land. Above land, the land warms up faster. Rising air makes our cumulus clouds during the daytime. Water cools down slower. So come nighttime, air above the land's cooler, above the water's warmer, and we have the air above the water rising, and we make cumulus clouds over water at night. Other things that cause air to rise, for example, a forest fire. All that heat, that air's hotter, it's going to rise. Eventually, as it cools, it will make clouds. Or anything else we can make a lot of hot rising air with. If you see a cloud like this, that definitely tells you something important. Go away. A nuclear bomb mushroom cloud. That's a cumulus cloud due to that hot rising air from the nuclear explosion. With mountains, where we have rising air, we'll tend to make clouds, maybe even storms, some rain. And then we get to the top of the mountain, down the other side. One, we dumped a lot of the moisture over here. Two, that air is sinking. As it sinks, it gets warmer. Any clouds to the left at that point are evaporating. So we have the orographic effect, rain shadow. Areas downwind of mountains tend to be dry. Areas upwind from the mountains tend to be wet. Here's an example where you can see this. These greener bands in here are areas with mountains, and then more tan desert beyond. Orographic effect, we're getting the wet on the mountain, dry on beyond in the lowland. Here's a different example of that phenomenon. This funny cloud here looks like a crash-landed UFO, but in fact we have a cloud, winds blowing. As that air rises up over the mountain, when it gets this high, it's cold enough, it's hit the dew point, and we start making the cloud. Wind blows on past, starts going down, and gets below the level of temperature at the dew point. So the cloud is constantly being formed here and evaporating here as the wind blows past. Also, as clouds blow over mountains like this, that creates waves in the wind, just like a river flowing over bumps gets waves in it. And so waves in the wind, once they've blown over mountains, can again, as they go up and down, go up. That may cross the point where the temperature is at the dew point, and clouds above that up bit, and then dip down again, and a bit with no clouds. So you can get these kind of lens-shaped or bars of cloud forming due to waves in the wind up and down. What about air mass collisions? The warm air, being less dense than cold air, will tend to move up. As it moves up, cools down. Great big mass of air, all cooling down. So this will tend to give us a big layer of clouds, stratus clouds, where this warm air mass moved up over the cold. It was said that it gets colder as you go up. Why? Well, rising air is under less pressure, it expands, and with expanding air, same amount of air in more space, cools it down. This is referred to as adiabatic cooling because it happens, you're not actually taking heat out of the total air, but with that change in pressure, you automatically get a change in temperature. Conversely, if you squish air down, you're warming it up. This is something that is important to keep in mind if you're pumping up a tire. You're putting air into pressure, pumping that tire up, and it can actually get pretty warm. This is especially important if you've got anything flammable nearby. There's sometimes a problem with that. Anytime air is expanding or contracting, expanding, it's going to cool off. Contracting, it warms up. How fast? Well, for dry air, this is referred to as the dry adiabatic lapse rate. Yeah, kind of big name, but basic idea. How fast does dry air change its temperature due to the change in pressure from moving up and down? Turns out it's about 10 degrees Celsius if you go up or down by a kilometer. But our water vapor, higher heat capacity, changes temperature more slowly, and what really slows it down is if we hit the dew point. Say we're cooling our air, lowering the pressure, and we get down to the dew point. Now we've got to deal with the latent heat. The water vapor is condensing from vapor to liquid, and as it does that, it has to release its latent heat. But our air was cooling, now we're releasing heat. It's not cooling down, it's staying the same temperature while that's happening. But it's still rising. So our air is cooling off much more slowly because of the moisture in it. So our wet adiabatic lapse rate, how fast wet air cools or warms due to pressure, is much slower, less. This is very, very important for what happens to the weather. In base idea, rising warm dry air will cool off faster than rising moist air. Sinking cool dry air warms faster than moist air. So our dry air adjusts faster. Our wet air does not adjust very fast, which means our wet air is going to be out of balance. Our dry air gets into balance much more quickly. Out of balance, that's what can give us storms. Okay, precipitation. This is water that reaches the Earth's surface in a liquid or solid form. This means that dew and frost are not true precipitation. Although we speak of dew fall, that's not really accurate. Dew and frost form directly on the surface. So it's water vapor contacting the surface and then forming into liquid or solid there, as opposed to, say, rain or snow, where we actually have the water or ice falling in the air. How this develops depends on where you are. In more tropical areas, of course it's warm, plenty of evaporation, and so you get lots of water vapor in the air pretty easily. Rising up, cools down, you can form clouds pretty quickly. Also, with all that evaporation, we get chunks of salt blowing around in the air from splashes of salt water. Water sticks to salt very well. So bits of salt in the air are very good condensation nuclei. And these clouds can develop fast, form quickly, and start raining and break up again in around a short period of time. Around here, often, as we get rising air, it actually has to get below freezing before we start to build significant cloud nuclei. And so, up at cloud level, it's typically snowing rather than raining. But as that falls, if the air below it is above freezing, it will melt and give us rain. If the air below it stays cold enough, then it can fall all the way to the ground as snow. And we see the snow rather than the rain.